adjust some of the ones that you missed.
You're the best friend.
I know. I know. Tell me things I know. And that's what I don't want to go on something new, and I don't want to leave questions out there hanging in the or hanging in your minds and not be able to answer them. So when we get to a test or quiz, you can perform to your best. And I want you to get that practice before the homework cancels out or whatever. But this one, we didn't talk too much about range, and I don't really like these questions that are in WebAssign, but it is something to think about. But what we're going to show you here, what I'm going to talk to you about right here, is not something that we always want to do. Okay? And I'll give you an example of why. But when I look at this one, okay, 9x squared plus 2, and they ask me what is the domain, okay? This is a polynomial function, and we talked about this yesterday. A polynomial function has a domain of all real numbers, okay? And the way we can remember that or realize that is when we're doing this information, when we're dealing with domains, what we're talking about is we're taking some function, don't care what it is, some function f of x, okay? And we're going to take some x value, okay? And that x value is going to be from the real number. So that's what that means. X is an element of the real number. And I'll plug that x value in. So any number you can think of off the number line, you're going to plug that in. It's going to be an input value, okay? And if it is part of the domain, it should give you an output number that is also an element of the real numbers. That makes sense? Okay, so if x belongs to the real numbers, if x is part of your domain, you should be able to plug that into the function, do all the operations that it says inside the function, it'll spit out a number, and that number should also be part of the real numbers. Okay? And if you think about this, okay, really what we're trying to exclude here are, right now, spell it right, imaginary numbers. Okay? If I plug in any x value there, anything you want, all the real number line. Okay? So again, imaginary numbers do not exist on the real number line. So if I put any real number that I want to in for x and I square it, do I get another real number back? Okay? So choosing something on the number line, square it, it gets you somewhere else on the number line. Multiply that by 9, does it put you somewhere else on the number line? Add 2 to it, does it still put you somewhere on the number line? Okay. Okay? So every single x value you can imagine, if you do these operations to it, you will still get back a real number. So input a real number, output a real number. Okay? And that means that our domain is negative infinity to positive infinity. You can choose anything that you want to for x, and you're going to get something back for your y value. Okay? Now the range is talking about what do those y values that you get back look like. Because you're not going to get back negative numbers in this case. Okay? For instance, if I try, no matter what number I try, okay, I cannot get at least 0 back. Plug in 0 for x. You square it, you get 0, right? Multiply by 9, you get 0, right? Add 2 to it, you get what? You get 2. Okay? 2 ends up being the smallest number that you can get back. Okay? The range, if I look at this graph, and this will be something that we get a lot better at recognizing and dealing with, because range is really hard algebraically to come up with. So we'll most of the time look at a graph and look at our techniques that we use for graphing to help us with the range. But if I look at this thing, basically x squared would look like that, right? Would you guys agree that this function is somehow related to x squared? Okay. Now what that 9 does is it takes every y value of x squared and makes it 9 times bigger. Well, if it does that, what's going to happen? Oh, that sucks. What's going to happen is, oh, I'm saving. So I got to click all the way over here. There we go. That's not what I wanted. Like, I don't know, I don't understand this thing. Like the touch screen on Everything that's white works, but everything up here is like 3 inches off. So get back that 9 is going to make your original parabola just a little bit skinnier, something like that. Okay? And that plus 2 is going to move it up 2 units. Does that make sense? If you're to graph this on your TI 83 or 84, hopefully you have some previous knowledge about transformations from Algebra 2. Okay? But if I graph this, let's get back to standard view here. Okay, there's your x squared, right? Well, 9x squared, you see how it just made it skinnier? Okay, and the idea is that this y value here on x squared is a 1. Well, on 9x squared, it's right there, it's 9 times bigger. Is that doable? Okay. If I look at the x value of 2 and I get a y value of 4, okay, then on that skinnier curve, that y value of 4 is going to be 9 times bigger, so I should have a value of 36. And if I look at an x value of 2, the y value here is 36. Okay, so that's all that 9 is going to do. And then the plus 2 is going to move it up 2 units. And now that is the graph that they're asking you to find the range for. Okay? Well, when I find range, I'm reading from the bottom up. Okay? And I'm looking at y values. So if I'm reading this graph from the bottom up, okay, what is the first y value you come across bottom up? 2. Okay? Now, is 2, that y value, is it on the graph? Yes. So answering that question, is it on the graph, says I include 2. Okay? Now going back to that picture, what would be the last y value you come across? Infinity. Okay? So we're going to look at 2 to infinity for that range. Okay? That's easier to do, easier to interpret if we have the graph with us. Okay? And that's kind of one of the things that we're going to focus on this class, is trying to develop that graph. 1, to help us out with the range. But 2, to teach us some techniques that maybe gets us the range without the graph. And we'll talk about those things as we move on throughout the year. There was one that was similar to that. Something like this. I want to talk about, I just want to create a new one. Let's go something like f of x was 5x squared plus 3, but they tell you your x's have to fall between those numbers. Okay. And then they ask you again what the domain is and what the range is. Okay. The domain question here, hopefully, is something that we understand pretty easily. If they did not give me this, say this was gone. My domain is all real numbers. It's a polynomial, right? But what they're doing with that there, 0 is less than x, or less than or equal to x, less than or equal to 3, they are telling me what my domain has to be. They're telling me these are the only x values you can plug in. Does that make sense? Okay. So that tells me, we call it a restriction or a constraint on our domain, but that forces our domain right now to be 0 to 3. Those are the only values that we're going to plug in. Okay. Now, just because this is it's the style of question. Everybody had the same question, just the 5 or the 3 was different. They asked for the range, and the best way to answer the range in this question, I think, is a graph. But we could do this. Somebody in the last class said, well, can't I just always do this? Can I plug 0 in as that number right there? I get 5 times 0 plus 3, and I get 3, right? So my range value starts at 3. And if I plug this 3 in, I get 9 9 times 5 is 45, plus 3 is 48. And I say, can't I do that? Because that gets me the same answer every time. And for this problem, for 5x squared plus 3 on that domain, yes, you can do that. Okay? But here's where I caution you and I say that's kind of a stupid thing to do. Because what if I start you off with f of x equals 5x squared plus 3, but now instead of going from 0 to 3, let's go negative 3 to positive 3. Let's say that's my new domain. Negative 3 to positive 3. So now if I plug in negative 3, negative 3 squared is 9, right? Times 5 is 45, plus 3 is 48. If I plug in positive 3, okay, so I plugged in that one first, and now I plug in that one second, now I get positive 48. Well, if I have an interval that starts at the same spot and ends at the same spot, that's just 1 point, right? Okay. Hopefully you realize that there's going to be more to this graph than that. Okay, if I look at this graph will look like (5x squared plus 3). This wasn't working last period, but see if it will this period. Yep. Okay. The graph that we're looking at is simply, zoom out there, just that graph. And you see how it stops, right? The height that it's stopping at up here is 48. I've restricted the domain, so it restricts the y values and the ordered pairs that I ultimately get back from that. Okay? But if I plug that number in, I got a positive 48, and got that one to be a 48. Okay? But is that telling me the range here? Is that telling me what the smallest y value is and what the largest y value is? No. Okay? It's just basically giving you that point there. You're evaluating that point, and you're evaluating that point. We need to be able to recognize and realize that that point there of 3 is still the smallest value on that curve in regards to its y values, and now 48 is the largest. Okay? So plugging in domain values, just arbitrarily plugging in domain values, is not the best thing to do in this case. Not plug in your beginning and ending domain values. The hope is that eventually we recognize, oh, well, that's just a parabola, but it's been moved up 3 units. So I know that the vertex is at 3. That's going to be the smallest y value. And then I can plug in this largest x value of my domain to get my largest y value. Okay? But those are all kind of tricks and techniques that we'll learn the more we see these types of things. Okay? And the first time, I don't know if a lot of people would have recognized that. Okay, so on your homework though, that was always that first number right there was always a 0, so you could just substitute. Does that make sense? But on a test or quiz, you might not be able to do it. So we have to analyze and think about what that graph looks like before we just start plugging away and finding y values. Okay, and that's what I want to hope to instill in you as we go through the years. Think about what you're doing before you do it. Okay, don't just start randomly doing work and not really knowing where that work's going to lead you. I'm anticipating maybe we had some questions towards the end. Anybody have questions on like 13, 14, 15, anything like that? 16? I like this one. McGoober, I think maybe I ought to give you a quiz over this question today. Or maybe tomorrow. Or maybe Friday. Or maybe both. Remind me before you guys leave. I got to give you your quizzes back. Well, I mean, they're already graded, so if you don't want it, you don't need it. But all right, so we've got this function, okay? Whenever we see a function, we want to first think about what its domain is. What values are we allowed to plug in? What real numbers what x values that are real numbers can we plug into that thing so that we spit out a real number, right? Okay, so we plug in an x number and get back an f of x that is also a real number. Well, hopefully you realize that if I plug in like -3, plug in -3 here, okay? What do you get back when you take square root of -3? Imaginary. You get a radical 3 times I, right? Okay. Now, if you plug in -3 in the bottom, you're going to get some number, right? Okay, I don't know what that is, but you'll get some number. Okay. Well, so you got I divided by some number times radical 3. Well, that's imaginary. It does not exist in the real number line. So we have to have a tool that allows us to kick that -3 out of our domain. Okay. And we don't want to sit here and try to think, okay, well, if -3 didn't work, does -2.99 work? Does -2.999 work? Does 3.1 work? Does -4 work? We don't want to sit here and think about all the numbers that may or may not work, right? That inevitably would be a very long, tedious process, and logistically doesn't make sense to do it that way. So what we do is we recognize that we can't take square root of negative numbers. Okay, we cannot take square root of negative numbers. So what we do then is we say, okay, if I can't take a square root of a negative number, then I need to force that expression, whatever it may be, because it represents just a number, right? That number cannot be negative. So I'm going to say that expression x cannot be negative. Well, making it equal to 0 or greater than 0 does it, right? If it can't be negative, then it could be 0 or greater. Okay? So we're going to do that. And hopefully, in this one, there's no additional algebra we need to do to solve for what x is. Okay, x has got to be greater than or equal to 0. Okay. Now the other issue in this problem, okay, is that if x is greater than 0, there might be division by 0 at some point. Okay. I'm not sure what number it would be right now off the top of my head, but we could probably plug something in here and get a 0 on the bottom, right? Some number that's bigger. Maybe I plug in 2 and I multiply everything out here, and it gives me 0 here. Well, square root of 2 divided by 0 is still a problem. Does that make sense? So we need to check this thing. 8x squared plus 7x minus 1 is not allowed to be 0. Okay. And the hope is that you understand that concept, but the reality is every single time you see a problem like this, if there's a square root, you always let the square root be greater than or equal to 0. Okay, and you solve. And if there's division, you always say that denominator cannot be 0, and you go through and you solve. Okay. There's one intricacy when the square root shows up in the bottom, but it's nothing that we can't work through. Okay. So if I go through and solve this, I'm going to use the a times c method, so I get -8 over here. Are there two numbers that multiply together give me -8, but x give me 7? 8 and -1. So now I'm going to rewrite this as 8x squared plus 8x minus 1x minus 1 cannot be 0. So we factor by grouping, right? Something we learned in chapter 1. And if you didn't take the time in chapter 1 to learn that, please do so, because that's going to show up in a lot of different problems. Okay? When you get to a calculus class, what's kind of problematic about calculus isn't the calculus, it's the algebra, because they jump around from question to question so much in one section. You might use this factoring technique in question 1, question 2. You might use quadratic formula in question 3. You might use rational root theorem. And they're assuming you've been to pre-calculus, you've been to trigonometry, so you have these tools, and you should be able to adapt and use them whenever you need to. Okay, so that is one thing that people in this class struggle with, is that once you learn something, they're assuming you learned it, and that you can use it and recognize when to use it at any time beyond that. Okay? I think sometimes maybe that's a bad assumption, but it is the way things are done. I'm going to look at these first two things and pull out an x, right? Or an 8x. Okay? And when I do that, I'm left with x plus 1. And these two things have a -1 in them, right? So plug that out, or pull that out, and I get x plus 1 again. Cannot be 0. So 8x minus 1, that factor, and x plus 1, that factor, those cannot be 0. So I get x cannot be -1, and x cannot be 1/8. Okay? Now, when we look at this, and this is where we got to be thoughtful, and we have to understand what that word meant, what and meant, okay? Because I can only plug numbers in to those x values in an original function if those x values are greater than 0 and they are not -1 or 1/8. Okay? So, what I like to do is always like to, especially with these types of questions, just quickly sketch a number line. Okay? And I'm going to highlight, I'm going to identify all the values that we just determined through our algebra. Well, we had 0 on there. We found -1. And we found 1/8, right? Scale's not right, but it doesn't really matter. We just put them in the right spots chronologically. Okay? This statement here says x has to be greater than or equal to 0. Well, graphically, it would be that information there, right? Okay? This stuff down here says x cannot be -1, so there's got to be an open dot there. And x cannot be 1/8, so there's got to be an open dot there. Okay? So I graph those things. And then I remind myself that I highlighted that word and both things, both situations have to occur at the same time for me to plug a value of x in. Okay? Now just think about this. -1 gives me an imaginary number right there, right? So automatically it is out of play. It also, when I plug it in, gives me 0. So imaginary number divided by 0. That's a huge issue, kind of twofold there in that situation. So -1 is not going to be incorporated, even though the algebra kind of showed that it might be something we want to deal with. Okay? We're only interested now in numbers that are greater than 0 and not 1/8. Okay? So to write this in interval notation, we start at 0. We're going to go up to 1/8. So we get just to the left of 1/8. Okay, we're going to exclude 1/8. We're going to jump over 1/8. And then we're going to go pass through infinity. And then when we're done with that, we're going to union. Okay, and that then ends up being that interval in which we have real numbers. And when we plug in here, we get a real number back. So anything out of this, these two intervals, okay, it's a real number. And when you plug it into g of x, it will spit back a real number to you. Okay. If you think about anything that is over in this range over here, a region, you're going to get an imaginary number here, right? If you plug in that number right there, the top is going to be okay. Square root of 1/8 is okay. You can do that. Okay? But I'm going to have the square root of 1/8 divided by 0. Can I do that? No. Okay? So that's why I have to have both pieces of criteria true. Because if it works up here, it may or may not work here. But if we use the and idea, if it's going to work up here, it will work down here. If it doesn't work up here, it's not going to work down there either. I think that's one of the harder questions because of that idea of being able to graph. My suggestion to you, do not look at that and look at that and try to instantly go from that information right now to an interval. Okay? Draw the picture first. Organize your thoughts first. Okay? You do that, 10, 15 times, maybe for this chapter, next chapter, following chapter, whatever. You do it enough, then eventually, yes, you can jump from your algebra to this. But I think it's so much easier and so less stressful if we just draw the picture. And it doesn't take that long to draw a picture, right? Okay. Now that stuff up there is working. I don't know. Other questions on there you guys want to talk about? 19. All right, so this is the one kind of intricacy with square roots that we got to pay attention to. Because we said in the last one, we always want to take square root and make it greater than or equal to 0, right? We can't take square roots of negative numbers. We've got to force that expression underneath to be greater than or equal to 0. But in this situation, okay, if I look at that square root and I allow that to be equal to 0, Okay? So I choose, and go ahead, let's go ahead and solve this. So I get 2 minus x is greater than or equal to 0, so x ends up being less than or equal to 2. Okay? If I go ahead and solve that, choose numbers that are less than 2. Well, if I choose 1, okay, 1 cubed is 1, right? Square root of 2 minus 1 is just the square root of 1, right? So I'm going to take 1 divided by square root of 1. Is that okay? Get a real number back, okay? What if I choose like 1.5? Okay? Well, 1.5, you can cube that. 2 minus 1.5 is 1/2. Square root of 1/2 is a number, right? So I should be able to take the numerator divided by the denominator and get a real number back, okay? But what other number is less than 2 that maybe pretty close to 2? Maybe I phrased that wrong. What number is less than or equal to 2 that is pretty close to 2? 2 itself, right? If I plug 2 in, 2 cubed is something we can do, right? But what's 2 minus 2 underneath? 0. Square root of 0. Can you take square root of 0 by itself? Yes, you can. Okay? Okay, so if I have 2 cubed, I get 8 up top. Okay? Square root, if I put 2 in there, square root of 0 is 0. I can do that algebra by itself. But can I do that algebra now? No. So what does that tell me I had to do with that value of 2? I had to exclude it. Okay? So when we see a square root in the denominator, okay, instead of saying 2 minus x is greater than or equal to 0, and I should probably not write the radicand or the radical symbol. So we just want the expression. The expression is greater than 0 because we want to make sure that the denominator does not become 0 itself. That's the only time that you would change that inequality sign. Okay? If it's in the numerator, it's always greater than or equal to. If it's in a denominator, it's just greater than. Okay? And in this case, we don't have to worry about anything else because there's with that x cubed, that's polynomial. So there's no numbers that you're going to plug in as a real number, cube it, and not get a real number back. Okay, so the x cubed doesn't provide any issues for us in regards to the domain. So now I say 2 is greater than x, so x is less than 2. That's going to be my domain. So what we would say in interval notation, if x is less than 2, we're looking at something like that. And then you can start trying some of those values. That's what I always like to do when I'm done. Hey, I don't like to do it, but it's a good idea. Start plugging some numbers that come from that range. Not say range, but that span of values, that interval, and make sure you can do it. You can do that math. Okay? If I take -5 and square it, or sorry, cube it, I get a number back. And then take 2 minus -5. Well, that's radical 7. I mean, I can take 125, -125, and divide it by the square root of 7. That's okay. That will give me a real number back, right? Okay. But if I try numbers that are outside that range, maybe I try like a number like 4. That's outside that range, right? Okay. Or outside that interval, that span. Okay. Take 4 and cube it, so that gives me what? 64. Okay. And then down here I get 2 minus 4. That's radical -2, right? Or square root of -2. And that brings in an imaginary value, right? So 16 divided by I radical 2 isn't from the real number line. So we have a problem there. So that's why 4 should be excluded. Okay? So I always like to try some numbers that I know should be in my solution. And I also like to try some numbers that are outside my solution to kind of verify that, yeah, I'm doing things right. Okay? And a really good thing to do, especially if your intervals are open or closed, whatever, doesn't really matter. But take those endpoints and plug those in and make sure it makes sense. And we're saying we should not include 2. So what happens if I did put 2 in here? I would get 8 divided by 0. Oh, we know we can't do that, and that tells us then that we should have had that parenthesis. Okay? I think plugging things, once you have an answer, plugging things back in is going to help you maybe reinforce the concepts a little bit more and understand it at a different level than just going through the work arbitrarily without thinking about what we're really doing. Does that help? Any others? We got some time left, maybe one more to do. Not, okay? 18. I'm going to copy this because the last class went in this one too, but we're not going to do the numbers that I have. So let me just change the 4 and the 2. Let's start with f of x equals, Addie, what was your 4? What was that number right there for you? 9. 9. And what was the 2? 8. Alright, so let's do that one. Alright, so again, we're trying to think about the numbers that we can plug in that will give me an output back, right? Okay, give me a real number as an f of x or as ultimately a y value. Think about that numerator. That numerator says x plus 9 squared. Okay? Think about any number you plug in. Okay, for x. If I plug in like 0, I get 9, right? 9 squared is 81. Okay, can I take 81 and divide it by anything? Is 81 a real number? Yeah. What about, let's try negative 9. Negative 9 plus 9 would give me 0, right? 0 squared is 0. Okay? You can take 0, you can divide by anything, except for 0. Okay? But 0 is a real number, right? Started with an x value that was real, negative 9, and got back a real number, 0. What if I try, like, 11? Plug 11 in there. Okay, I get 20 back, right? 20 squared is 400, right? Is 400 a real number? Yes. Okay? So my hope is that we're realizing that this thing here is a polynomial function by itself. Okay? So if I just had, if the question was just that, your domain for that would be all real numbers, right? Okay? You can plug in a real number, alter it through these operations, and your output is a real number. So nothing in that numerator really provides any problems for us. Okay? What happens is that the denominator is going to provide us problems because the denominator can never be what? 0. Okay? But the square root can never be what? We don't want this. We don't want this here to be a negative number because when that brings a negative number, then it incorporates imaginary values. Okay? So there's two components to this question with that denominator. One, the 8x minus 1 has to be a positive number, right? It has to be greater than 0. Okay? Well, let's just write greater than or equal to 0 right now. If we were just looking at that denominator, if that was just a function, f of x equals the square root of 8x minus 1, that denominator, or that 8x minus 1 would have to be 0 or greater, right? If it was negative, we have the square root of some negative number, and that's imaginary. Okay, so that would be a problem. But because it's in the denominator, okay, there's an issue with that right there, isn't there? Because if I allow this, go ahead and solve this, you get x to be 1/8, right? X to be greater than 1/8. Okay. If I solve that, if I say x is greater than or equal to 1/8, okay. As long as it's greater than 1/8, this is going to be okay. I'll get a number up here, just a real number up here, okay, and I'll get a real number down here. But that real number, if I let it be greater than or equal to 1/8, if I let that real number of x be 1/8, I would get the square root of 0, and the square root of 0 is 0. So the numerator would be some number, I don't know what it is, but this one would be 0, and can I take a number and divide it by 0? No. So what we have to do, when the radical is in the bottom, instead of saying greater than or equal to 0, we just say it's got to be greater than 0. And now we've got x to be greater than 1/8. And that's going to be our interval for that domain. It might be a good idea for you, okay, to write just some pointers down. Say, if, let's say, if f of x incorporates division, okay, set denominator not equal to 0. So then maybe an example says, like if I have f of x equals ax plus b over cx plus d, then I set cx plus d cannot equal 0 and I solve. Okay. If f of x incorporates even roots, set radicand greater than or equal to 0. Okay. Except if root is in denominator, then set radicand greater than 0. Maybe an example of that would be, f of x equals square root of ax plus b. Then that should provide ax plus b is greater than or equal to 0. Okay. And then we had another example says f of x equals maybe a over, and it could be just any expression. It's ax plus b over square root of cx plus d. Then you take cx plus d, that expression, and you just make it greater than 0. So having maybe that information, I know it's a lot to write maybe, but having that maybe at the top of my paper or somewhere in my notes could be something to reference back to and say, okay, I'm not sure what to do on this problem. Where is the radical? Where is their division? And then I can go back and say, okay, there is division. So I set the denominator not equal to 0. Okay, but maybe there's a root in there as well. So then it would tell me to do that rule too. Okay, I don't like to provide you with very extremely concrete rules like that because every once in a while maybe that gets broken at some point, or maybe there's a little intricacy to it. But it also, I think sometimes people memorize that rule and then become very robotic and don't think about what they're really doing and the implications of what they're doing. But that might be kind of a saver for some of us if we're so struggling with that idea of when to set equal to 0, when not to set equal to 0, that kind of stuff. And I want to make sure, and that's why we're spending a lot of time on this. Like if you were in, like say you were on Rhodes' campus or OSU's campus or Toledo's campus or whatever, you're probably talking about this for maybe half a day, okay? But I know how important it is and how people have struggled with it in the past and how much we use it beyond this, that I think it warrants a little bit more than that, okay? So please understand that and please take the time to, if you do get confused or are having issues, ask those questions.